Hello, I'm Samantha Scales, and this is my Lab 2 report on projectile motion. The goal of this lab was to analyze the two-dimensional motion of a thrown projectile, which for me was a crumpled paper towel ball, by comparing real video data to two computational models built in GlowScript. The first model applies Newton's second law using gravity only, and the second model adds a drag force. I wanted to determine which model actually predicts the real motion and quantify how much of a role air resistance plays for an object this light. There are four core equations behind this lab, and each one of them comes with specific physical reasons. The position update formula, final position equals initial position plus velocity times the time step, comes straight from the definition of velocity as the rate of change of position. If velocity is roughly constant over a small time step, this is just rearranging that definition. The velocity update formula comes from the momentum principle, which is really just Newton's second law written for changing motion over time. Final velocity equals initial velocity plus force over mass times the time step. The reason this works is that the force causes acceleration, and acceleration is the rate of change of velocity. So multiplying acceleration by a small time step tells you how much the velocity changes. The force of gravity, negative mg in the y direction, is constant because near Earth's surface, the gravitational field doesn't meaningfully change over the scale of this experiment, so it acts as the same on the ball at every point in the flight. And the drag force, negative bv squared, in the direction velocity exists because air resistance comes from the object colliding with air molecules. The faster it moves, the more molecules hit it per second, and the harder each collision is, which is why the force scales with velocity squared, not velocity itself. The negative sign in the unit vector makes sure it always opposes whichever direction the object is currently moving. Here's what I found. My experimental ball landed at about 0.622 meters, while the gravity-only model predicted about 0.608 meters, which is almost exact. The drag model predicted only about 0.396 meters, which is undershooting by about 35%. The gravity-only model also matched the max height closely, and so this tells me that for a 1 gram ball thrown at about 2.65 meters per second over such a short distance, air resistance was actually too small to detect. For my system and surroundings, my system is the paper towel ball treated at a point mass, and the surroundings are Earth providing gravity at 9.8 meters per second squared, and the air providing drag based on the air density. For my procedure, I recorded the throw with a calibration object in frame, then used tracker to mark the ball's position frame by frame and extract velocity. My initial conditions were a mass of 1 gram and a starting height of 0.216 meters, and an initial velocity of 1.07 meters per second horizontally and 2.42 vertically, a total launch speed of about 2.6 meters per second at 66 degrees above horizontal. Here's a frame from the video showing the ball mid-flight tracked against my calibration stick on the floor. Here I built two GlowScript models with identical starting conditions. The only difference is the drag term. Model 1 sets b to 0, so only gravity acts, while Model 2 includes the full drag force. Both update velocity and position using the momentum principle and stop the instant the ball reaches the floor. This graph shows all three trajectories together on one plot. The light green is experimental, the navy is gravity only, and the teal is gravity plus drag. You can see the experimental curve tracks the gravity only model almost exactly in the same shape and landing point, while the drag model clearly falls short, predicting both a lower max height and a shorter range than what I actually observed. For my possible errors, there's a few things that can explain the gap between my drag model and reality. Air currents in the house, slight inconsistency in my throw, the camera angle, and the fact that the crumpled paper towel doesn't have like a perfectly consistent shape or cross section could have affected my data. The first question asks whether my model reaches terminal velocity. Terminal velocity happens when the drag force grows large enough to exactly balance gravity, making the net force zero and the acceleration zero. At that point, the object falls at a constant speed instead of continuing to speed up. My gravity-only model never reaches this because there's no drag term to balance gravity at all. The velocity just keeps increasing the entire time it falls. My gravity plus drag model does predict a terminal velocity, though, found by setting the drag force equal to gravity and solving for v. V terminal equals the square root of mg over b. Plugging in my numbers gives a terminal velocity of about 3.17 meters per second. But my ball only launched at 2.65 meters per second, and the whole flight lasted just over half a second, nowhere near enough speed or time for drag to actually catch up to gravity. So neither of my models actually reached terminal velocity during this experiment. If I wanted to test for it directly, I need to drop the object from a much greater height then look at a velocity versus time graph. Terminal velocity would show up as the curve flattening into a horizontal line. The second question asks what would happen if I threw the same ball straight up with the same initial speed instead of at an angle. If all of that 2.65 meters per second goes straight up, the rise time is velocity over g, which gives about 0.27 seconds to reach the top. From there, I calculated the max height above the launch point and added that to my starting height of 0.216 meters and used the total height to find the fallback time to the floor. Adding the rise time and fall time together gives a total flight time of about 0.613 seconds. Compared to my original throw, the straight up throw actually takes longer to hit the ground. And this makes sense because in my original throw, part of the initial speed was being used to move the ball horizontally, which doesn't help it stay airborne any longer. But thrown straight up, every bit of the same speed is dedicated entirely to fighting the gravity and gaining height, which means more total time in the air before it comes back down.